Welcome to Maths with AJD. In this video, I'm still working on some structured questions. For instance, here I'll be talking about die fairness hypothesis testing. Based on the question I have here, the table below shows the observed and expected frequencies of a die thrown 120 times. Face of die 1 to 6, and then you have the observed 23, 19, 21, 15, 23, 16. And the expected, of course, when you roll a die, you expect uh you expect each of the faces to show up at 20 times. If you throw it 120 times, right? You expect each of the faces to show up 20 times each. That's like 1/6 or 120 each. So the first question is you're required to calculate the coefficient of association or discrepancy of thrown die. Two, test the hypothesis that the die is fair at 0.05 significance level. So let's go for that. So first part is to find, or rather to calculate the coefficient the coefficient of association. Okay, you can see that as a discrepancy, right? Of the thrown die. So you need to invoke the formula. The formula in that case is uh okay. Let's just go for that and say that the coefficient of association, the coefficient of association or the chi-squared statistic, the chi-squared statistic. So the chi-squared statistic is what is known as the coefficient of association. That is chi-squared measures how much the observed frequencies, how much the observed frequencies deviate from the expected frequencies. Okay. Now, it is calculated using the chi-square formula. This chi-squared equals summation of O sub I minus E sub I all squared divided by E sub I. Basically, O here is this is the observed frequency for each outcome. Observed frequency, observed frequency for each outcome, right? And E is the expected frequency for each outcome. Frequency, expected frequency for each outcome. So that goes. So with this, we can go ahead and use what we have. It's always nice if you can do a table. If you can do a table, it makes things pretty easy instead of doing these computations one after the other. So let's put those things in a table. So first we have the face. Second, the we have the observed, right? We have the observed and then we have the expected. Observed, that is O, I, and then we have the expected, which you can call EI. So that's the basic thing we have. So we have six faces, 1, 2, 3, 4, 5, and 6. Okay. And then for the expected, we have okay. For the expected 23, 19, 21, 20. Oh, okay. For the observed rather, 23, 19, 21 on phase 3. On phase 4, we have 15, 23, 16. 15, 23, 16. Okay. And of course, the expected is 20 in each case. So that's easy. So just 20 all the way. So now we need, from the formula, right? We need the square of the difference between observed minus expected. So let's do OI minus EI first. Okay, well, since that's like where our computation starts, so I want to change the color. So we have OI minus EI. And of course, we can have O, okay. Um, okay, we'll come for that later. So OI minus EI simply means 23 minus 20, that's 3. 19 minus 20 is minus 1. Okay. 19 minus 20 is minus 1. Okay. 21 minus 20 is 1. 15 minus 20 is 5, is minus 5. 23 minus 20 is 3. 16 minus 20 is minus 4. So that we can now have the square as OI minus EI all squared. So 3 squared is 9. 1 squared is 1 squared is 1. 1 squared again is 1. 5 squared is 25. 3 squared is 3 squared is 9, sure. Minus 14, minus 4 squared is 16. Okay. So um then EI um okay, this is EI squared, right? So we also need is that necessary? Thinking of doing this separately. So expected I in each case is 20. Okay, so let me just leave that and then just do it outside of that. Okay, so let's just do it outside of that. Now we can go back and invoke the formula. So we can now say we have chi squared. Chi squared equals summation of all OI minus EI all squared divided by EI. Then we sum all of that together. So that means we have chi squared of so OI minus EI. So we have 911, 2591. So that's 9 over 20 plus 1 over 20 plus 1 over 20 plus plus 25 over 20 plus 16. Oh, sorry, this is 16. This is 16 actually. 25 over 20, 9 over 20, 9 over 20 plus the last one, 16 over 20. So we can easily say that is 9 plus 1, 10, 10 plus 1, 11, 11 plus 9, 11 plus 9 is 20, plus 25, that's 45, 45 plus 10, 55 plus 6, 61. So that's my smart way of trying to do that. Okay, so we have 61 over 20. That's more or less like um we divide by 2. This is 30.5 divided by 10. So that'll be 3.05. So this is 3.05. That's the coefficient of association. So that's what we need for the first part, right? Find the coefficient of association or discrepancy. So you can conclude that and say, therefore, the coefficient of association or the discrepancy of the thrown die is 3.05. So let's go for the next part of the question. It says, test the hypothesis that the die is fair at 0.05 significance level. So to test the hypothesis, that the die is fair, at the 0.05 significance level. Okay, of course, we already know chi-squared. Okay, let me change this. We already know chi-squared uh test. That's the test statistic. We already know that is 3.05. So we have that. Okay, or before I even begin to say that, let's set up the whole thing, right? Let's set up the whole thing. Let's set that up. So this is about the hypothesis testing part now. That's part 2 of the problem. So the first thing is we state step 1. Step 1, state the hypothesis. State the hypothesis. Okay. So we have the null hypothesis, which is H naught. So that is simply that the die is fair. Simply, that's the null hypothesis, that the die is fair. That simply meaning that any observed differences are due to random chance. Okay, then that's the null hypothesis. That we can have the alternative hypothesis. Hypothesis, which is H not, I mean H1 or HA. So let's say H1 here. So that's just the opposite. That just simply means the die is not fair. The die is not fair, meaning that the observed differences are significant. So that's the first part, talking about the hypothesis. Now we go ahead to talk about the degrees of freedom. So to determine the degrees of freedom. Okay. So there are 6 possible outcomes, 6 phases. There are 6 possible outcomes. So there are 6 possible outcomes. So the degrees of freedom DF equals 6 minus 1. That is 5. So that's the degree of freedom we need there. Then next, we go for step 3. Step 3, find the critical value. Find the critical value. Okay. So we now say for a significance level, of alpha equals 0.05 and 5 degrees of freedom, 5 degrees of freedom, 5 degrees of freedom, the critical chi-squared value is 11.07. That's if you check your table, look using this value of alpha, which is 0.05, and degrees of freedom, which is 5. So you're going to get 11.07 like that. So that's the critical value. Now we have calculated the chi-squared, right? From the test statistic. Now we have got the critical value. So we have basis for comparing both of them. So let's go for that now. Step 4, we compare the calculated chi-squared value to the critical value. So the calculated chi-square value is a test statistic, right? So we can say that, okay, well, we can state that, right? We can say chi-squared tests is 3.05. That was all we got. And chi-squared critical, that's the one from the table, is 11.07. So the one from test is smaller. So in that case, let's see the decision we have to make. Now here we say the calculated chi-squared statistic is 3.05, which is less than the critical value of 11.07. So that takes us to step 5. So in step 5 now, we calculate the p-value. Well, I think with what we already have, there's no point. We don't necessarily need to calculate the p-value. This is just an alternative. But let me just do the two. You can choose your choice normally. So calculate the p-value, which is absolutely not necessary, but it's an alternative. So the p-value associated with a chi-squared, the chi-squared statistic of 3.05 and 5 degrees of freedom is approximately 0.692. So with that now, we can go for the decision. The decision is next step. That's step 6. So what decision do we make based on the foregoing? So we can say the calculated, since the calculated chi-squared statistic, which is 3.05, right, is less than the critical value, which is 11.07, and the p-value of 0.692 is greater than alpha, which is 0.05. Okay. Then we accept the null hypothesis. That is, we fail to reject the null hypothesis. Okay. We fail to reject the null hypothesis. That means we accept the null hypothesis. Generally, right, once your calculated value is less than the critical value, then you accept the null hypothesis. But if what you calculate is bigger than what you get from the table, then you reject the null hypothesis. Okay. So same goes for p-value. So your p-value should be, once your p-value is greater than your significance level, you also accept the null hypothesis like that. All right. So in conclusion, right? In conclusion, so we can go for the conclusion. So the test results suggest there is no significant difference. There is no significant evidence. There's no significant evidence to conclude that the dye is biased. There's no evidence to conclude the dye is biased. Therefore, we accept the null hypothesis indicating that the dye appears to be fair, based on the observed data. So that takes us to the end of the question. Really interesting one at that. So a lot of practice. And interestingly, if you have options of choosing between this kind of question and that question on there's a lengthy question in this same section, right? Which is about correlation, and you do a whole lot of computation and you are prone to making mistakes. So it's better you choose this one ahead of that. You only choose such tasking questions if you don't have a choice. So if you have not subscribed to this channel, be sure to do that. Hit the notification bell so you can always get alerted when a new video is released. Comment, tell me if you want me to teach a topic or solve a problem, and also share so that more people can have access to this educational content. See you next time. Bye.